Hello friends, so today this is part 2 for the questions which were asked in the 2019 mains, and in this part 2 we are going to solve 10 mains questions. In the first part also we solved 10 mains question from the year 2019. So in the first question it states that a uniformly charged ring of radius 3a and total charge q is placed in xy plane centered at origin. A point charge q is moving towards the ring along z-axis and has a speed v at z is equal to 4a. The minimum value of v such that it crosses the origin is. In this case, we are given that we can just draw an approximate figure for that in xy plane, and it is centered at the origin. So we can just draw an approximate figure. So this is our x and y axis, and we have a uniformly charged ring. So this is our ring and it is centered at the origin, and total charge q is placed in xy plane center. Okay, so this is having a charge of q, and we have a point charge q which is moving along z-axis. So obviously z-axis will be perpendicular to this plane, and it is said that at a distance of 4a. Okay, suppose this is our distance, and please remember this will be vertical to this xy plane, and this distance is our 4a from the origin, and at this point the velocity is given as v. So this is our test charge q. So we have to find the minimum value of v such that it crosses the origin. Okay, so it should be able to cross the origin, which we are able to. We need to find out that particular velocity. And in this case, we have to remember that the charge on the ring is also plus q, and the point charge is also given as plus q. Okay, so it means there will be force of repulsion between the two, or we can say the ring is going to produce a potential barrier along the z-axis, and there will be, because of you can say along the z-axis, and therefore we need to find out the value of the potential at this particular point, and based on this we can then use the energy principle, that energy at z is equal to 4a, and it's just crossing the origin. So energy are there using energy conservation, and it is going to solve the question. So we start with that we are given that ring produces a potential barrier along z-axis. Along z-axis, and we can say we can find out this potential. So we can see electric potential due to ring due to ring at any point on z axis and its radius is given as 3a. Okay, so radius is given as 3a. Electric potential due to ring at any point on z axis, at any point on z axis, and we can write the equation that V of z will be equal to 1 upon 4 pi epsilon naught charge q divided by this comes as z square and plus our radius that is given as 3a whole square and its square root. So we can just write it as 1 upon 4 pi epsilon naught. This comes as q and we are having z square plus 9a square and its square root. And we can say the potential energy U of z or directly let's use the conservation of energy. Okay, conservation of energy, and there will be 2 points. One will be our origin and another will be our this z point. Okay. So initial energy will be our z. So we can say initial energy at z is equal to 4a. Let us call it as u of I, which will be equal to, it is having a velocity there, so it will be our half mv square plus energy because of this potential. So we can say this will be our charge multiplied by the potential at the value of z, which is given as 4a. And similarly we can write our final energy that will be our origin, final energy at z is equal to 0, and here we require that it should just cross the origin. Therefore we can say that the final energy will be only because of the potential, that is charge multiplied by potential at value of z is equal to 0. So because we want that the charge should be just able to reach the origin, therefore we can assume that the velocity at the origin is equal to 0. So we have to remember this thing, that we want that charge just reach the origin. So from here we can say our velocity v will be equal to 0 at z is equal to 0. So it means all kinetic energy or initial energy will be our directly related with your potential energy. So we can just equate the initial and final energy, and we can say our initial energy is equal to our final energy, which gives us initial energy was our half m v square plus q multiplied by potential at z is equal to 4a is equal to Q multiplied by potential at Z is equal to 0. And we already know the equation of the potential that is dependent upon the Z. Therefore, we can just modify the equation. We get this as half m v square plus Q and potential at 4a. So we get this as 1 upon 4 pi epsilon naught. Q, substituting value of Z as 4a, we get this as 4a whole square plus 9a square and its square root will be equal to Q 1 upon 4 pi epsilon naught. Now value of Z is equal to 0. So this comes as Q upon 9a square and its square root. Now it is simple calculation. We are interested in velocity. Therefore we can modify, make some arrangement in this equation. So we get half m v square is equal to, we are going to get a factor that will be constant, common, that will be over Q square upon 4 pi epsilon naught, and this will be 1 upon 3a minus this comes as 16 plus 9, that is 25a square, giving us 5a. And we can solve it. We get this as Q square upon 4 pi epsilon naught. LCM will be over 15a rather, and this will be coming as 5a minus 3a, which will be giving us 2a. And we can just cancel the terms. This goes by 2 and 2 goes by 2. Therefore we get our velocity will be equal to, we are having here Q square, and this comes as m pi epsilon naught multiplied by 15a. And so this will be our velocity and its square root, and Q square we can take common. Let's see the options which are given to us. Okay, they have not cancelled 4, so we can keep the 4 as it is. So they have not cancelled it, so let us keep the 4 as it is. So here we have 2, here we have 4, and here we have 2, and therefore we get this as 15, and here will be our now 4. Sorry, this 4 is here. So we get this as 4 pi epsilon naught and multiply by our m, and 2 to 4, so this also comes as 4. I think hopefully this matches one of the options. Therefore we get this as m. Okay, they are segregated 2 and 4. Okay, let's do that. So we can write this as square root of 2m, and inside bracket we are left with now square divided by 4 pi epsilon naught, and this is our 15a, and here we are left with 2, and this becomes half. So here we are having, I think 15 to, this should be option, but D should be the correct one. Option D is correct. Next question. It was asked in the 2019 mains, and it states that shown in the figure is a shell made of conductor. It has a inner radius A and outer radius B, carries a charge Q. At its center is a dipole P as shown. In this case, we have to find out various things, and three options, that is related with surface charge density, and one is our for electric field. Okay. And in this case, we are, remember the figure is given to us. We are given that the inner radius is our A, outer radius is our B, and there is a dipole inside, and along with that there is a charge Q at the center. Okay. So, and here we are given that center also has a dipole. So first of all, let's find out what will be the electric field, okay, outside the shell. And electric field outside the shell. And outside the shell basically means that our small r is greater than our B. So we can use Gauss law, which gives us that for a closed electric field is equal to charge enclosed divided by epsilon naught. And we are given a dipole, and dipole we know that the net charge associated with the dipole is 0. Net charge is equal to 0. But along with the dipole, there is also a given charge at the center, which is our Q. Therefore, our charge enclosed will be equal to our Q. Therefore, we can say electric field outside will be equal to 1 upon 4 pi epsilon naught, and this comes as Q upon R square. And this is equivalent or same to the electric field because of a point charge at the center. Okay, so we can say this is electric field due to point charge, and point charge is our Q at the center. So therefore option B is correct. Option B is correct. Next, we are interested in surface charge density, and it says that the surface charge density on the inner surface of the shell is 0 everywhere. Okay. On the inner surface. So therefore, one second, surface charge density so we can say that the electric field, which is because of the dipole inside the conductor, okay? And the conductor, inside the conductor means radius is in between A and B. So we can say electric field from the dipole, which is given as P, inside the conductor, and inside the conductor we basically means that our radius is greater than A but less than B. And if we want that this electric field should cancel each other, okay, so we can electric field from the dipole inside the conductor should cancel, then the inner surface must develop a induced charge, okay, so that that creates a induced electric field which will be the negative of the dipole inside, okay. So to cancel, then the inner surface must develop an induced surface charge which we can call as sigma inner, and this will be basically having two coordinates, that is both theta as well as our phi, that creates a field which we are going to call as E induced, and that should be equal to negative of the electric field that is being created by the dipole, and this is our inside. And we know that the dipole field is non-uniform. Dipole field is non-uniform. So because of the non-uniformity of this dipole field, it also requires a non-uniform induced charge. This requires a non-uniform induced charge. But we know that total induced charge is 0, but total induced charge is equal to 0, or we can write it in the form of integral also. So integration, and this is with respect to the only inner surface. Inner surface, sigma, that the charge density for the inner, and with respect to a small area dA will be equal to 0. So means option B is false. Not option B, but option D is false. And next is surface charge density on the inner surface is uniform and it is given as q by 2 upon 4 pi a square. But we have already shown that the net induced charge on the inner surface is 0. So the surface charge density is not uniform, or we can say not equal to any expression that is inclusive of this q. So from here we can draw another conclusion, that net induced charge on inner surface is equal to 0. Therefore, surface charge density is not uniform. Surface charge density is not uniform, or rather we can say that not equal to any expression with q. So therefore option A is also incorrect. Option A is incorrect. And finally we come to the option C, which states the surface charge density on the outer surface depend upon the P, which is our dipole moment. And we know that the outer surface is going to carry the entire charge q, because the dipole does not contribute to net charge. Okay. And the inner induced charge is already 0, we just concluded it. Therefore we can say the outer surface adjusts such that the field outside is consistent with the charge q, dependent upon charge q. Okay. So the inner dipole has no influence, or we can say the outer surface charge does not depend upon the dipole, because the net charge because of the dipole is 0. So the outer, our surface charge density is only dependent upon q, not on the dipole. You can say that outer surface must carry all charge q. All charge q, and we also know that dipole do not contribute to net charge. Dipole do not contribute to net charge. Therefore our outer surface is independent of the dipole. Then we can say that outer surface does not depend on P, or we can simply write the formula that the charge density at the outer surface, it will be dependent upon only our q and our 4 pi b square, and this will be our uniform. So option D is also incorrect. Sorry, it's not option D. but option C is also incorrect. Option C is incorrect. Next question. It says that a solid conducting sphere having a charge q is surrounded by an uncharged conducting hollow spherical shell. Let the potential difference between the surface of the solid sphere and that of the outer surface of the hollow sphere is V. If the shell is now given a charge of minus q, the new potential difference between the same two surfaces is. So here we are given, you can say, two cases. In the first case, we are having a solid sphere and the solid sphere is having a charge plus q, and around it there is a shell, and there is uncharged. Okay, so initially there is no charge itself of the shell. In the second part, we are having, and the potential difference between the two is given as V. In the second part, we are still having a shell, sorry, a sphere, and the sphere is having a charge q itself of its own charge, and on this hollow spherical shell now a charge of external charge of minus 4q is given. So in this case we have to find out what will be the new potential difference. Initial potential difference is given as V. So initial potential difference is given as V. Okay. So for the sake of simplicity, let us say that the inner radius of, or we can say the radius of this sphere, if this is center, let us suppose this is given as R1, and radius of the inner side of this shell is our R2, and radius of the outer side is, let us suppose, R3. So let me write it. So we are having a solid sphere and its radius, let us suppose, is given as R1, and we are having a hollow shell, and please remember that is a conducting hollow shell. So we are having a hollow shell, and in this hollow shell its inner radius let us suppose is given as R2, and outer radius is given as R3. Outer radius is given as R3. Okay. And this hollow shell is conducting. And because of the, you can say, charge which is given to the sphere, our sphere, which is our plus q, so we are having plus q charge on the sphere. So So from the inner side we are going to get a induced charge that will be minus q, and on the outer surface we are going to get a charge of plus q. So because of this, the total charge, or we can say the net charge on the shell A is equal to 0. So we can say that due to charge plus q on solid sphere inner surface of the shell, inner shell surface is going to have a charge of minus q, and outer shell surface is going to have a charge of plus q. But on the shell this total will be equal to 0. So initial potential difference is given as V. So let us calculate what will be the value of this V. Initial potential difference. Initial potential difference, which we are given as V. So first of all, we are going to find out the potential at the surface of solid sphere due to all charges. Similarly, we are going to find out the potential at the outer surface of the shell due to all charges, because the potential difference is given only between the outer surface and the solid sphere. So we can say potential at the surface of solid sphere due to all charges. All charges, and let us call this as V solid, and this V solid will be equal to kq upon the radius of the sphere plus k minus q radius of the inner surface plus kq radius of the outer surface. And similarly, we can find out at the outer surface of shell due to all charges. All charges. Let us call this as V outer, and this V outer will be our kq upon R3 plus k minus q upon R3 plus kq upon R3. And from here we can easily see that these terms cancel out. So on the outer we get this as kq upon R3. Now we can find out the potential difference. Initial potential difference, which is our V, will be equal to our V of solid minus V of the outer. we already know the equations. We can write it as kq upon r1 minus kq upon r2 plus kq upon r3 minus kq upon r3, and here this kqr3 cancel out, so we get our v is equal to, we can take kq as common, this comes as 1 upon r1 minus 1 upon r2. So this is our initial potential difference. Let us call this as, okay, it is given V, let us keep it VL. Now we are given that the outer shell is given a charge of minus 4q. Shell is given a charge minus 4q. Sphere, its own charge will be still plus q. So we can say sphere is having a charge of plus q, and shell is going to have a charge of minus 4q. And because of the, you can say, you can put it like this, that shell is our conductor and it still surrounds the sphere. So therefore the induced charge on the inner surface must still be minus q. Okay, we have to remember that, because charge on the sphere is plus q. So based on this, we can say that induced charge on inner surface of shell will be equal to minus q. Now the outer surface is having a charge of minus 4q and inner is having minus q, so we can find out the net charge on the outer surface. So we can say net charge on outer surface will be equal to minus q, and this will be our minus 4q minus of minus q, and this comes as minus 3q. Now we are going to find out new potential difference. New potential difference. So first of all, we are going to find out new potential difference at the surface of solid sphere, and similarly for our outer surface, outer shell surface. So you can say for solid sphere, and in this case also due to all charges. All charges. So we can say this will be solid, and let us call this as nu, will be equal to kq upon r1 plus k minus q upon r2 plus k minus 3q upon r3. And next is for outer shell surface. Outer shell surface, and once again due to all charges. Let us call this as we call this as V outer nu. Will be equal to KQ upon R3 plus K minus Q upon R3 plus K minus 3Q upon R3. And here this KQ and this cancels out. So we get this is equal to minus 3KQ upon R3. Now we can find out the potential difference. So we can say V nu is equal to V solid nu minus V outer nu. So here we can just now substitute the values, and we get V solid nu is our KQ upon R1 minus KQ upon R2 and minus 3KQ upon R3, and this comes minus of minus 3KQ upon R3. So this will be coming as plus, this goes with this, and we are left with only, we can take KQ as common, so this comes 1 and 1 upon R2, and this is same as that of our V, okay, because we just calculated this here. So therefore we can say that our V new potential difference will be equal to our V. So option number D is the correct. Option D is correct. Next question. It states that the given graph shows variation with distance from the center of, okay, so figure is given to us, and we are given the graphical representation of the electric field, or it can be the potential also. Both are given. Here Y is not mentioned, so it can be our electric field or it can be the potential also. And you can say this is our spherical shell, and it is also a, okay, so it is graph for two things. One is our spherical shell and the one is for the charged sphere. So from the graph it is quite obvious that this is the representation of our a uniformly charged spherical shell. Okay, potential of a uniformly charged spherical shell. Okay, I think there is no need to, because this is a standard result. You can say option B is the correct one. Because if you want to do, we can still make a wild guess for that, and electric field inside a, you can say, sphere will be 0 and potential will be constant, and outside it is going to behave like a exponential decreasing. Okay. Next question. It states that a point dipole P is equal to minus P naught x unit vector is kept at the origin. The potential and electric field due to this dipole on the y-axis at a distance d are respectively. Take V is equal to 0 at infinity. So we are given a dipole, and that dipole is placed at the origin, and we have to find out the electric field due to this dipole, potential as well as electric field on the y-axis. Okay, we can just draw an approximate figure for that. And so this is our x-axis, y-axis, and the dipole is, its direction is also given, that is minus x unit vector. So obviously, so this is our dipole, and we are going to have plus q, and we are going to have this as a minus q, because the direction of dipole is in the minus x unit direction. Okay. This is our dipole P, and we need to, okay, so for a point which is at a distance d, let us, this point we call as point A, and it is at a distance of d. Okay. So in this case, let us write the coordinate of our point P. Point P, for the sake of convenience, let us say this is our minus a comma 0, and obviously it will be plus a comma 0. Okay, we are only considering the two axes, x and y. Z will be obviously 0, and because of this we can just draw an approximation of the electric field. So because of the positive charge, we are having electric field. Let us suppose we call this as our E positive, and because of the negative charge, we are going to have electric field in this direction. Let us call this as E negative. And using the parallelogram law, we can say our net electric field will be something in this direction. Or we can just divide this both positive and negative into the components. So vertical component are going to balance each other, and the net will be along the positive x-axis. That will be our direction of the electric field. And let us say, or we can say we are given that the dipole moment P it is given as minus P naught x unit vector, and we assumed that the coordinate of plus q is our minus a comma 0 and our minus q is our plus a 0. Therefore, we can write that the formula for the dipole moment according to this charge distribution, you can say, therefore dipole moment, which is our P, will be equal to our charge, and this comes as our minus a minus of a, and this is our x unit vector. So we get that our P will be coming as minus 2a q, and we have this as x unit vector. So from here we can find out our charge, that is our q will be equal to, in terms of P naught, we get this as P naught upon 2a. And the potential at point A potential at point A, that will be our, you can say, the algebraic sum of the potential due to plus q as well as potential due to minus q. So we can say potential at point A, let us suppose that our VA will be equal to our due to plus charge and plus due to negative charge. And this will be equal and opposite. Okay, so we can write this will be our, if V positive, and we can just call this as minus sign. So as the charges are equal and the distance, suppose this is our r distance, so this will be also our r, and this we have our a, and this is also our a. So distance of point A from the respective charges will be also equal. Therefore we can say that respective contribution from plus q and minus q are equal and opposite. Therefore we can write that our potential at A will be equal to 0. Now we can find out the electric field at this A point. Electric field at A, and whose coordinate are 0, d. So net electric field will be electric field due to positive charge plus electric field due to negative charge. So this can be written as q upon 4 pi epsilon naught, and this comes as a square plus d square 3 by 2, and this comes as multiplied by minus 2a, and we have this as x unit vector. And in terms of the dipole, we can write this will be equal to our minus p naught divided by 4 pi epsilon naught d cube, and we have our x unit vector. Okay. The standard formula for the dipole field, electric field due to dipole, standard formula for dipole field it is given as E is equal to 1 upon 4 pi epsilon naught, and this is our 3, and we have this P dot R, and our R unit vector minus P divided by our R cube. But along the y-axis, this R unit vector is perpendicular to our dipole. So we can say this P dot R is equal to 0 on y-axis. Therefore, we can say that our electric field will be equal to minus of P divided by, and the R is now equal to D, so this comes as 4 pi epsilon naught D cube, and we are already given this comes minus of P naught x unit vector divided by 4 pi epsilon naught, and this is equal to D, which comes as P naught x unit vector divided by 4 pi epsilon naught D cube. Okay, let me write it separately here. So we get electric field is equal to P naught x unit vector, and this is 4 pi epsilon naught and D cube. But from the looks of this formula, it looks like that both electric field and the dipole are in the same direction. But if we look at our initial figure, from here we can easily see that our electric field is towards the right side, whereas the dipole moment is towards our left side. Therefore, this will be having a net negative sign. So we have to remember this part. And based on this, we can say that our potential will be equal to 0, and our that electric field is minus P upon x unit vector, which is not mentioned in the question, but anyways, that's a simple direction. So option B is the correct one. Option B is correct. Next question. It was asked in the year 2019 mains, and it states that determine the electric dipole moment of the system of 3 charges placed on the vertices of an equilateral triangle as shown in the figure. So here we are having a equilateral triangle. Charges are placed, one charge is at origin, so this will be 0, 0, and another charge is placed on the right side, length is L, so this comes as L, 0, and it will be placed at a height certain, which we can calculate later on, and will be equal to L by 2. We have to remember that. Okay. So we can just say that our minus 2q is going to have a coordinate L by 2, and the height will be given as minus 3 by 2 times L. Okay, we can just use the Pythagoras theorem to find out the height. Now we can use, there are 2 approaches to solve the question. The first is by using the dipole moment formula, okay, which is much more easier and convenient also. So we can use the dipole moment formula, and that formula states that our dipole moment P will be equal to summation, and this is our product of our charge multiplied by the distance, that is our r vector, and this is for various values of I. We start from 1 to n. Okay, number of charges. Here the value of n is equal to 3. Okay. And so we can just write this formula according to the given question, and we can say that our dipole moment P will be equal to charge. Let us call this point as our A, this is our B, and this is our C. So we get this is Q, and our distance our RA plus Q distance our RB, and the charge next is minus 2Q, and distance is our RC. Now we can easily find out their respective values. So first value we are interested in finding is Q times RA. So this comes as Q, position of RA is our 0, 0, and this comes as 0, 0. Second is our Q times our RB, which comes as Q times L, 0, so which we can write as QL, 0. And finally, we can write this as minus 2Q multiply our RC, which comes as minus 2Q, and our RC is our L by 2, comma square root of 3 by 2 multiplied by L. So if you multiply it, we get this as minus QL, comma minus QL, and we have this square root of 3. Now we are going to simply add their vector positions. Okay, so we can say that our dipole moment P will be equal to, first is our 0, 0, plus second is our QL, 0, and third is our minus QL, minus QL square root of 3. And we can add our x component as well as y component separately. So we get this as 0 plus QL minus QL, and next comes as 0 plus 0 minus QL and square root of 3. So here this QL and QL cancels out, so we get this will be equal to our 0, minus QL square root of 3. Therefore, this is our x component, or we can say our I, and this is our y, or we can say this is our j. So this gives us that our P will be equal to minus QL square root of 3 and j unit vector. This is one of the approaches which we can use. And the second approach is by considering the, you can say, two dipole charges. So we can just draw an approximate figure. Answer will be same in both cases. And here we are having minus 2Q. This is plus Q, and this is also plus Q. And let us call this as point as A, this is point as B, and this point as C. Okay. So we have two dipoles, and each dipole is plus Q and minus Q. Other one is also plus Q and minus Q. So this we are considering the two dipoles, each of plus Q and minus q. And we can just find out this angle will be over 30. So we can find out net dipole because of the respective. So this will be having a p dipole in this direction, this will be also p here. Dividing into components, we are going to get this as p sine of 30, and this is also p sine of 30. And along this direction, we are going to get this as 2p cos of 30. And obviously, so these two will be balance each other. Net will be over 2p cos of 30, which will be giving us same answer. Okay, so this is our, you can say, second approach which we can use. Second approach. Answer in both the cases will be same. And so we get this will be equal to our option number C is the correct option. Option C is correct. Next question. It says that an electric field of 1000 volt per meter is applied to an electric dipole at an angle of 45 degree. The value of electric dipole moment is 10 raised to power minus 29 coulombs per meter. Coulombs meter. What is the potential energy of the electric dipole? And we already know the direct formula for potential energy of dipole is minus P dot E, which is our minus PE cos of theta. Theta is given and everything is given to us. So we simply substitute the values. So we know potential energy of dipole, that is given as U, is equal to minus P dot E, which comes as PE cos of theta. And we simply substitute the values. We get this as U will be equal to minus, dipole moment is 10 raised to power minus 29, electric field is given as 1000, and we get this as cos of 45, which will be 1 upon square root 2. And this will be approximately equal to minus 7.071 into 10 raised to power minus 27 joules. So option number D is the correct one. Option D is correct. Next question. It states that two electric dipoles A and B with respective dipole moments dA as minus 4a qa I unit vector and dB minus 2a qa I unit vector are placed on x-axis with the separation r as shown in the figure. The distance from A at which both of them produce the same potential is. So we are given the dipole and we have to find out the distance from A which produces the same potential. So let us redraw the figure, and we are having, let us suppose this is our A and this is our B. Distance between them is given as capital R, and we say that the potential at point is at a distance of x. Let's suppose this is 0, and here the potential is same, which is at a distance x from A. So from the other side it will be over R minus x. And so we also know that electric potential has a direction towards the dipole from the point. So it means the potential due to point A and point B will be opposite in direction. So direction will be opposite. And we are given that at A, we are given a dipole dA whose is 1 minus 4 QA I unit vector, and we have at B we are given as dB, which is our minus 2A QA, and this is also our I unit vector. And okay, so we know the formula for the potential with respect to the dipole. So we can say potential due to dipole on its axis. Potential due to dipole on its axis, that is given as V and is equal to our K, and this comes as P dot R divided by R square. And the R is the distance, so we can simplify. This will be equal to V is equal to, so let me write it with respect to the distance. So we can say V at a distance of x will be equal to over K, and this comes as P divided by x square. And we can just you can say divide this equation into 2 because we have two dipoles. So we can say that V, let me keep this as V only, it will create confusion otherwise. So V because of A is equal to V because of B. So we get this as minus V 4QA divided by distance is x square is equal to minus 2QA and divided by R minus x whole square. And now it's quite simple. It will be just a quadratic equation and we can just solve it. So we get 2 upon x square is equal to 1 upon R minus x whole square, which gives us 2R minus x whole square is equal to x square. So from here we can say that our x will be equal to plus minus square root of 2 and R minus x. So from here we can say that we have two solutions. One solution is our x is equal to plus square root of 2 R minus x, which can be written as square root of 2 multiplied by R minus square root of 2 multiplied by x. So now we can easily find out our value of x. So from here we can take x as common, and this comes as 1 plus square root of 2 is equal to square root 2 multiplied by R, which gives us that our x is equal to square root 2 divided by 1 plus square root of 2. So this is from the first part. And similarly from the second part we get our x is equal to square root of 2, and this comes as square root of 2 minus 1. So we have the 2 points, 2 values of x. Okay. And from 2 values of x we can say that our option A and B will be correct. Option A and B are Next question. We are given, for a uniformly charged ring of radius r, the electric field on its axis has a largest magnitude at a distance h from its center. Then the value of h is. So here we are given that we have a uniformly charged ring and electric field on its axis has a largest magnitude. So we can just draw an approximate figure for that. This is our ring and radius is given as r. Sorry. And on its axis at a distance. So we can just, this is our r, and at a point, suppose x in general, and here let us suppose the electric field is given as E of x. In this particular question, the value of x is equal to h, but we are going to generalize the formula, and we already know the formula that the charge is, it is uniformly charged. Let us suppose that is given as q. Therefore we can say electric field on the axis of a ring. Electric field on the axis of the ring, and we can write that formula that our E of x will be equal to our k, and this comes as q divided by x square plus r square 3 by 2 and multiply by x. And it is given that maximum value of E of x is when x is equal to h. So we are given that maximum value of E of x is at x is equal to h. So we are going to find out the maximum value of E of x, and which is quite easy. We are going to simply differentiate it with respect to x and put that derivative equal to 0. So we can just differentiate it. We can say our dE upon dx will be equal to kq, and denominator will be our x square plus r square, which comes as whole raised to power 3, and this we get our x square plus r square and 3 by 2 multiplied by 1 minus x, and this is our 3 by 2, and this comes as x square plus r square 1 by 2 and multiply by 2x. And if we put this derivative equal to 0, we are only interested in the numerator part, and we get from here that x square plus r square 3 by 2 minus this comes as 2 goes with 2, this comes as 3x square, and here we have x square plus r square and 1 by 2 is equal to 0, and this gives us that we can just factor out x raised to power 1 by 2, and if we factor out x raised to power 1 by 2, sorry, we factor out x square r square whole raised to power 1 by 2. So this gives us inside will be left with only x square plus r square minus 3x square is equal to 0. And we can just, this comes as r square minus, this will be equal to our r square minus 2x square is equal to 0, which gives us that x square is equal to r by 2, or which gives us, square, and x is equal to r by square root of 2, and this value of x is equal to h. Therefore we can say our h is equal to r square root of 2. Therefore option number A is the correct one. Option A is correct. Next question, and it states that in the given circuit the charge on 4 microfarad capacitor will be, we are given the circuit, it's quite simple circuit. We have to find out the charge on this 4 microfarad, and we have 10 volt source. Okay, so we can just, first of all we are going to solve this parallel circuit, and this will be resulting us, let me draw an equivalent circuit. So we are going to get this as, let us call this as C1, C2, C3 and C4. So we have C1 and the parallel of C2 and C3, let us call this as C equivalent, and it is in parallel with C4, which gives us this circuit. So we can say our C equivalent, and this C equivalent is our parallel combination of our 1 and 5, which is directly summation. So this comes as C2 plus C3, which comes as 1 plus 5 microfarad. So we get our C equivalent will be equal to 6 microfarad. So this is about 4 microfarad and this is about 6 microfarad, and this we already know is our 3. So we have a 10 volt, and this 10 volt is in parallel with our C4. So here we are going to have a 10 volt, as well as here also we are going to have a 10 volt. Okay. Now this C1 and C equivalent are in series with each other. So here also we can find out the equivalent capacitance, and we are going to get a circuit which is having now only one, you can say, capacitance. Let us call this as C equivalent prime, and here also we are going to have a 10 volt in parallel with this, and we have our C4, and finally we have a 10 volt supply. So we can say our 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C equivalent, this is prime. So we can say 1 upon 4 plus 1 upon 6. So we get this as C equivalent prime will be equal to, this comes as 624, 6 plus 10, so this will be coming as 24 by 10, which gives us 2.4 microfarad. So based on this, we know our C equivalent and we know our V. Therefore, we can find out the charge on C equivalent. So we can say charge on C equivalent, let us call that as a Q. Then this Q will be equal to our C equivalent prime multiplied by voltage, that is 2.4 multiplied by 10, and we get this as charge on C equivalent prime is will be equal to over 24 microcoulomb, and this 24 microcoulomb will be charged on this our C equivalent, and the C equivalent is a series combination of 4 as well as 6. So it means this 4 will be also having a 24 microcoulomb, and 6 is also going to have a 24 microcoulomb, because both 6 and 4 are in series, and in series the charge is same. Therefore we can say the charge on 4 microfarad will be equal to, let us suppose Q4 will be equal to 24 microcoulomb. Therefore option D is the correct one. Option D is correct. So this complete all the 10 question, and this was the part 2 of the year 2019, and in this we solved 10 questions, and all these 10 questions from mains only. There are some questions left, so we are going to do a part 3, and if required we are going to do part 4. So this completes all the 10 questions. Thank you.